Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we talk about another important parallel pattern, merge sort. We're going to talk about merge sort, but before that, let me very briefly remind you what are the other parallel patterns that we have covered in this course. We started with the reduction, an operation that reduces a set of values to a single value. Remember that the operator that we use needs to have certain properties like associativity, commutativity, and identity value. And the reduction, as you may remember, is a key parallel primitive. We discuss implementations of reduction that are divergence-free, because this way we can maximize warp utilization and consequently we can maximize the performance on the GPU. The next parallel pattern that we covered is histogram computation that frequently use primitive for reducing the dimensionality and extracting notable features of the data sets. We discussed about histogramming, where are the applications where we can find it, typically in image and video processing. And remember that what we do in histogram is accessing the input data, and based on the value that we read from the input data, we update one bin or counter in the output histogram. We have to be careful and avoid data races when in parallel implementations, for example, on GPU. To do so, we have to use atomic operations. And atomic operations, as you may remember, have the key drawback that they serialize the execution when there is an atomic conflict, but we also discuss as well interesting and useful optimizations that can definitely alleviate this drawback of the atomic operations. Then we covered the convolution, which is widely used in signal processing, image processing, video processing, and computer vision, and also very much used in an important type of neural networks these days that are the convolutional neural networks. As you may remember, to calculate the output values in a convolution, what we do is applying a filter or a mask on the elements of the input, and we obtain partial products and finally a weighted sum that gives us the output value. Here you can see one example for a 1D convolution, and this is another example for a 2D convolution. Remember as well that the good way of optimizing the performance of a convolutional layer on GPUs is lowering the convolution to a matrix multiplication, such as this example that we have on the slide. After that, we covered prefix sum or scan, an operation that takes an input array and an associative operator and returns an output array that is the result of recursively applying the associative operator on the elements of the input array. Remember that we talk about the exclusive and inclusive scan, and we discuss different ways of implementing the scan operation on GPUs using a hierarchical approach. This is the scan add version. We also discussed the reduce scan version. And as the basic algorithm, we talk about the Cogistone parallel scan algorithm. In the next lecture, we talk about the sparse matrices. Remember that a sparse matrix is a matrix where most of the elements are zero, and these represent opportunities in the sense that we can save a lot of space in memory or memory capacity. We don't have to store the zeros. We also don't need to load the zeros, and we don't need to compute with the zeros. By accessing the compressed representation of a sparse matrix from memory and operating with it entails certain challenges. In this slide, you can see how we could implement the sparse matrix vector multiplication when the matrix is compressed with the CSR representation. After that, we were talking about graph processing, and in particular about the breadth first search algorithm. Remember that breadth first search is an algorithm that we use to discover what are the neighbors of a specific source node and what's the distance to all other nodes that belong to the same graph from this source node. We discussed the challenges that we have when implementing graph processing algorithms on GPU, but we also we talk about the hierarchical approaches that we use to optimize the performance of BFS on GPU. We talk about this two-level hierarchy of queues where we have one first level in the shared memory is what we call the block queue, where threads insert the elements that will have to, the nodes that will have to be visited in the next iteration of the algorithm. That's what we call the output frontier on an iteration. After enqueuing output nodes or nodes to visit in the next iteration in the block queue, we have to spill those contents to the global queue. After that, redistribute to the available workers. And we also talk about a hierarchical kernel arrangement as a way to minimize as much as possible the synchronization needs. If the size of the frontiers, the size of the queues is not too large, we can use a simple approach where a single thread block uses intra-block synchronization, thus saving the kernel termination and the overhead of relaunching a new kernel. If not, we'll have to go for kernel 2, where we have to relaunch kernel. But remember that we also discussed a more efficient version that saves this kernel termination and relaunch by using persistent thread blocks. So this has been also so far regarding the parallel patterns. Today we talk about a new parallel pattern that is called merge sort. Merge is an operation where we take two sorted arrays or two sorted lists as the input, and we generate one single output list that is combined and sorted as well. Observe that there's going to be an order relation here. For example, one element, so that elements will be sorted based on this relation, for example, less than or equal to. And we may require this merge sort operation to be stable, that is, maintaining the relative order of elements which have the same value or the same key. Observe as well that we are talking about lists. In the examples that we will cover in this lecture, we will only talk about lists with simple elements, just one value. However, this list can also contain like tuples of elements with different, each tuple with different values, and one of them being the key. In the end, we are going to focus today on how we sort the input arrays based on this key. And there might be also one preference. For example, the elements of list A go before the elements of list B when they have the same value. We are going to make this assumption as well in our examples. Merge is an important building block for sorting algorithms, and it's also frequently used in the reduce step of MapReduce frameworks. However, implementing a parallel implementation of merge is pretty challenging due to the dynamic nature of data accesses that are going to be challenging to obtain maximum efficiency when accessing the memory by exploiting locality. We are going to discuss what the problems are and what could be potential optimizations as well. Okay, so let's start with a simple example. As I said before, there is an order relation, for example, and that's what we are going to consider in this lecture, less than or equal to in the sorted list and in the merge list. Observe that here we have two input lists, A and B. A contains 5 elements, B contains 4 elements, thus the output C is going to contain 9 elements. So we focus on a stable sort, which means that we are going to keep the relative order of the elements of the same value. For example, this 10 will always go before this 10. And also, whenever A and B have elements of the same value, the elements of A go first. That means that these 10 will go before these two 10s in the final destination. So, observe as well that there are some, we have to compare elements from the different arrays in order to perform the merge operation. And in this case, we find that the smallest element among all the elements from A and B is this one. So we place this one, then we place this 7. Observe that this 7 is also equal to this 7 here. But due to the fact that we assume that elements of A go before elements of B, we first place this 7 in the output array C, then the next 7, and then these 3 elements, 8, 9, and 10 from array A, and finally the last 3 elements from array B. Implementing a sequential sort is relatively simple. It's a quite simple code indeed. Here we can see the example. We start with the indices to A, B, and C, all of them equal 0. And then we start going over the two arrays A and B, comparing values from array A and from array B. And depending on what's the smaller is, or if it's equal, then we will choose the element from array A we write to the output. So for example, in the very initial iteration, we have I equals 0, j equals 0. These are the indices of A and B respectively. We compare A0 and B0, and we see that A0 is smaller. So we place it in array C. Then we increment, in this case, the index I and the index K, and again, we compare. These two are the same, but because the elements from A go first, we place the D7 in the output position, C1 in particular, and then we move to the next element. So we increment I and we increment K. And again, we compare. In this case, the element B0 is smaller than the element A2 from array A. So we place in the output in K equal to, we place this 7 coming from B. So we increment, in this case, J and K. We again compare now element with value 8, and the next elements from matrix A as well. And we go to the next part of the code. In this next part of the code, we have completely finished with one of the input arrays. In this case, array A. That's why I is equal 5. So I is equal to the size of the input array. And what that means is that we have to copy the remaining part of B into the output C. And that's what we do for K equals 6, 7, and 8. And this way we obtain the sequential merge. One important or interesting observation here is the complexity of this sequential algorithm. As you can see, the complexity is O m plus n. So if we want to come up with a parallel implementation of the merge sort algorithm that is work efficient, we should shoot for this complexity m plus n. So let's start discussing how to implement this merge operation in parallel. First thing that we may try to do is a scatter parallelization. Remember that in a scatter parallelization, what we do is dividing the input across the available workers, in this case, the GPU threads. So that would mean that each thread takes a section of the list A and a section of the list B, and then they find the element locations in list C. So for example, we could assign these two elements to thread 0, these two elements from array A and these two elements from array B to thread 0, these to thread 1, these to thread 2, and so on. However, the problem here is that the destination of an element of A or an element of B depends on the elements of the other list. And also depends on the elements of both lists that have been assigned to other threads. So for example, the relative order of these two elements, 7 and 8 here, is going to be quite difficult to find because 8 has been assigned to one thread, thread 1, while this 7 has been assigned to a different thread, thread 0. So in order to do like the right operation and to write the elements at the corresponding place of the output array, we will need to communicate across threads in some way. And that's probably pretty challenging, and we don't have a systematic way of doing this communication and the parallelization. So because of that, we try another approach that seems to be more reasonable for this parallel primitive. In this case, what we do is partitioning the output list equally among the threads. And now each thread collects input elements for its section of the output from both A and B input arrays. For example, thread 0 is going to collect these elements from array A, these elements from array B, and place them in the corresponding positions of the assigned section of the output array C. These could be the elements that thread 1 needs to read from array A and place them in the output array, and these are the elements that thread 2 takes care of. So the range of input elements to be used by each thread is a function of the input elements. That's something that we already know, but it's going to be more interesting after this observation. For any k such that k is between 0 and m plus n, that is k is the index to the output array C, we can find I and j such that k equals I plus j, while I is the index of array A and B is the index of array B. So, for example, for this k equal 3, we have I equal 2 and j equal 1. So these I0 plus J0 are equal 3. That is exactly the value of K0. Or for K1, that is equal 6, we find I1 equal 5 and J1 equal 1. Or for K2, that is equal 9, we have I2 equal 5 and J2 equal 4. So for an element CK, where k is referred to as its rank, I and j are referred to as its coranks. Observe that the rank of an element of the output array is the sum of the coranks to from the input arrays A and B. So in our gather parallelization, each thread gathers the elements of a continuous section of the output. So all threads identify the starting and ending locations of the continuous sections of the inputs A and B that they will use. So we need to have an input identification and partition by finding the core ranks. And all threads perform the merge for their sections in parallel. So each thread will execute the sequential merge in its own section. So now let's recap. Observe that we have assigned 3 different parts of the input array C to threads 0, 1, and 2. What these threads 0, 1, and 2 have to do is to identify what are the limits of their section. For example, for thread 0, it will start in k equals 0 and it will finish in k equal 3. For thread 1, we start in k equal 3 and we finish in k equal 6, and so on and so forth. And then based on these ranks, for example, k0 equal 3 or k1 equal 6, we have to identify, we'll have to find, or each thread will have to find the associated core ranks, which are the I and j that sum together are equal to the corresponding k and are within the bounds of the 2 input arrays A and B. For example, for k0 equal 3, we find we obtain I0 equal 2 and we obtain J0 equal 1. So let's see how we have to calculate these core rank values. The core rank values of a prefix string leading to the kth output element is a pair of I and j values that specify the rank values of the prefix strings of A and B that are used in forming the output prefix string leading to that kth output element. For a given output prefix string of rank k, its core rank values can be found by searching I and j such that k equals I plus j, and these 2 conditions here happen. Element A of I minus 1 is less than or equal to bj, and bj minus 1 is less than ai. So that's what we are going to do in the core rank calculation. But finding the core rank values for different threads is probably not a balanced process if we do a, let's say, linear search, because the search range for a prefix string in a subset is a subset of that of a higher rank one. For example, if we think about these two ranks, K0 equal 3 and K1 equal 6, the ranges, the search ranges in matrix A, sorry, in input A and input list B for K0 equal 3 are smaller than the search ranges for K equal 1. As you can observe, the thread that obtains the current values for this K1 will probably have to go through a larger section of, at least in this case, input list A than the thread computing the current values for this K0 equal 3, as you can see in the example. So finding A2 less equal than B1 and B0 less than A3 needs a smaller search range than finding A4 less or equal than B1 and B0 less than A4. So what we are going to do in order to accelerate this search and reduce the computational complexity is to use a binary search or an n-ary search for the I and j values to minimize the effect of the increasing search ranges. And this way, we can reduce the computational complexity from ON to O log n. So in that's going to be the search ranges of in this case for K1, and this is for K2. So the current function that we define, as you can see it here, it takes the rank that for which we want to use, we want to find the current values, and then pointers to the input arrays A and B and the sizes of arrays A and B. This current function is going to return the I corank, and the j corank is easily derived as k minus I. And this is our function. Let's analyze it by using one simple example. Observe that we start initializing I and j, and we also use two other variables that are I low and j low that are going to define the range of the input A and B where we are doing the search. Then there is this variable delta that we are going to use in the binary search to change the indices that we check, and then there is a Boolean active variable just to keep track of iterations and check when we have to finish the computation or the process. So this is how we are going to call the current function for K0 equal 3. And in the iteration 0, we start assigning so when we start the execution of this function, we assign the initial values to I equals 3, j equals 0, and then for I low equals 0 and j low also equals 0. So now we compare elements I and j to 0 and to the maximum value that they may have, and we also compare the corresponding elements of the input lists A and B. So in this very first iteration, I is greater than 0, j is less than n, and I minus 1 is greater than bj. So if we see that this 8 here for it's this A2 here is greater than this B0 here. So we go through this path and we update the delta value in the corresponding way. After that, we update the values for j, for I, for j low, and for I low correspondingly. So in this case, delta equals 2. These are the updated I low and j low. These are the updated I and j. And then we go to the next iteration, iteration 1. In iteration 1, we are going to take this path here because j is greater than 0, I is less than m, and bj minus 1, so that is b1 is greater or equal to ai. So it's greater or equal to this a1 equal to 7. So that's why we calculate using this expression here, we calculate delta, and we use this delta to update the indices I and j. And then in iteration 2, what we observe is that none of the two conditions here are fulfilled. So we go through the else path of this if-else statement, and finally we make active equal false. So what that means is that we will get out of this while loop and we'll return the core rank I that is equal to for this specific example. From this core rank I equal to, we can calculate the core rank J that equals 1. So in the basic parallel merge algorithm or implementation, each thread is going to be in charge of a continuous section of the output. So we need to find what's that section exactly. We know that it's defined by this k current and this k next. They define the beginning and the end of the corresponding section. In this example, this is the section assigned to thread 1. And from these two k values, k current and k next, we obtain the core rank values, I current, I next, j current, and j next. And these values are going to give us the exact area where the output needs to, so where the threads need to search in the input arrays A and B. And this is the code of the basic parallel merge. Observe that we are dividing the whole output array among the available threads. This is the thread identifier. Based on this thread identifier and based on the size of the output, m plus n, and the total number of threads that we are using, we obtain k current and k next. Using this k current and k next, we call the current function such that we obtain I current and I next, and then j current and j next. These define the ranges, the sections of the input lists A and B that we have to look for, and then we can perform the sequential merge. Each thread individually performs the sequential merge for the output section that has been assigned to it. The problem with this implementation is that it has uncoded memory accesses. For example, in the first read of thread 0, we read element A0. In the first read of thread 1, we are going to read element A2, and in thread 2 is going to read element B1. And then for the writes happens exactly the same. The first element that the thread 0 is going to write is this Z0. For thread 1 will be this C3, and for thread 2 will be C6. So as you can see, the accesses are going to be uncoded because these neighboring threads or adjacent threads are not accessing adjacent memory locations. The solution is to collaboratively load sections of A and B into the shared memory and perform a tile merge kernel. Because once we have loaded sections, continuous sections of A and continuous sections of B into the shared memory, threads can access shared memory and find the core ranks and then perform the sequential merge using the values in shared memory without having to incur these undesirable uncoded memory accesses. So let's take a look at how we implement the tile merge kernel. So in the beginning, what we have is these two input lists, A and B in global memory, output list C will also be in global memory, and then in shared memory, we are going to have some reserved space for tiles from A and B. But the very first thing that we have to do is finding what are the current and next ranks for each different thread, for each individual thread block. What we are doing here is dividing the whole input into different sections, and each of the sections of the output are assigned to each of the available thread blocks. In our example, we have 3 thread blocks, 0, 1, and 2, and this is how we split the output array C among these thread blocks 0, 1, and 2. So after having found the ranks for these blocks 0, 1, and 2, we have to find the core ranks in the arrays A and B. And then we can start copying tiles from A and B to the shared memory. This is what block 0 is going to copy for a start. This is for block 1, and this is for block 2. Soon after that, we have the threads of each block going through the elements of A and B that are now in shared memory in these tiles. They start comparing them. They are actually executing the actual merge operation and writing to the output in the corresponding places. We are going to see how exactly in the next few slides. And this is these are the elements from A and B that block 1 is handling and writing to the output section, and this is for block 2. So in this tile merge kernel, we assign output sections to the thread blocks. Each section, we should make sure that each section is large enough. It has at least a few thousand elements that are reasonable size of the section. Then we will have a leader thread in each thread block performing the binary or NRE search to identify the input sections to find what are the core ranks. Then it will communicate the current values to the other threads in the block, and then each block can iteratively generate the output section. In each iteration, the threads of the block load collaboratively one tile from A, one tile from B into the shared memory, and they perform the merge operation using the values in shared memory. Each tile should have at least a few hundred elements. That's a reasonable size. In the end, the exact size that we will use depends on the available shared memory that we have, depends on the number of threads that we are using per thread block. But as you know, typical numbers of threads per block are something between 32, which is a minimum recommendable, the warp size, up to 1024. So that's why it makes sense that each tile is at least of a few hundred elements. Next, we divide the output tile into subsections and assign them to the threads. So then each subsection should have at least a few tens of elements such that each thread can work with another. But as you see, we are dividing the output into sections that are assigned to the different thread blocks. Then we divide each of these output sections into tiles. We operate, we calculate, we find what are the values in the output tiles using input tiles in shared memory from A and B. And inside each thread block, we also divide the tiles into the available threads so that each thread can perform a sequential merge. And this way, all threads perform sequential merge operations in parallel using the elements of the input tiles. So as we have seen, first of all, we have to identify the k-current and k-next for each of the thread blocks that are involved in the merge sort operation. Then we have to find what are the current values, because these define what are the input subarrays for block 0, for block 1, and for block 2. So these two pieces here, these two sections here are the input subarrays for block 0, this section here and this section here for block 1, and these are for block 2. And this is how our code looks like. The merge tile kernel, we first start allocating memory in shared memory, and we say allocate like a large tile, and we divide it in two pieces of tile size that are going to be used to store the tile from A and the tile from B. We have to obtain for each thread block what's the starting point for the current block and the starting point for the next block, because they define these are k current and k next. In this code, we call them C current and C next, because they define what are the bounds of the section that has been assigned to one specific thread block. And then we have the leader thread, in this case, thread with thread index equals 0, that executes the core rank function for both C current and C next. And then it obtains, remember, with this core rank function, we obtain I So what thread 0 does is storing the I current and the I next into shared memory. It's simply writing them in two positions of this AS array in shared memory that is going to be used later to keep the tile from array A. But for now, we use them to write the current values for communication with the other threads of the block. So that's why we need to synchronize here. Right after that, all threads of the block read AS0, read AS1, write them into the A current and A next. This way, all of them know where the input tile from A and the input tile from B start and when they finish, where they finish as well. And then we have to synchronize again, because now these two positions, AS and AS0 and AS1, are going to be overwritten with values from the tile coming from global memory. So that's what we do next, is loading the tiles. That this block 0 or threads in block 0 read the whole tile from array A or list A, write it to share memory. Same for list B. This is what block 1 does with the section, the tile from list A, from list B, and this is for so this is for block 2. And this is the code for the loading tiles operation after having, initialized these different variables that define the length of the section in C, in A, in B, the total number of iterations based on what's the tile size that the thread block will have to perform. We start this while loop for the total number of iterations. First of all, the threads of the thread block go to list A, read one tile, bring it to the shared memory, and we do the same for list B, and then we synchronize. After that, we generate the output tile, or we start generating the output tile based on the values that we already have in shared memory coming from lists A and B. So, for example, in the case of block 0 threads are going to consume all these range of elements here from the tile of from tile AS, these ones from the tile BS, and write them to the output. And this is for block 1, and this is for block 2. Now, one thing that we have to observe here is that in reality, we are likely not consuming the whole input tiles that are allocated in shared memory, but only part of the tiles. So that's why we want to keep track of how much of the tiles has been consumed. That's why we use these variables A consume and B consume, because we need them to keep track of what elements from the input have already been copied or have already been placed onto the output, and start from there. So this is the next part of the tile merge kernel, where we partition the tiles among the threads. Remember that the input tiles that are already in the shared memory are going to be distributed across the threads that belong to the same thread block, and this way they can perform a sequential merge on the pieces of the input that have been assigned to them. So that's exactly what we do here. We know exactly what's the so we know what's the size of the tiles that we are dividing now among the threads of the same thread block, of the same block. So for each thread with a given thread ID, the subsection of the output array C that is assigned to them is given by this C current and this C next, and using this C current and C next, each thread individually finds the corresponding core rank values. In this case, A current, B current, A next, and B next. And by using them, the thread can perform the sequential merge on the subsection that was assigned to it. After that, we update the corresponding variables that we are using to control the access to the data structures. The performance of this kernel, that is like a relatively simple version of the tile merge kernel, can be improved further if we generate the output section in shared memory as well. We would need to reserve another tile for the output in shared memory. This way, all threads write first to shared memory, and after that, we can have coalesced accesses. We can move the output tile from shared memory to the global memory by doing coalesced memory accesses. That's an optimization that is not covered in detail in this lecture, because in reality is pretty much related to other ways of using the shared memory that we have discussed in previous lectures. So now in the next iteration, in iteration 1, we have to load again new tiles from the shared memory. But now remember that there is part of the tiles that have been consumed and another part that is not consumed. And that's what we have to take into account, because we would need to start copying the tile from here, or from here, or from here, or from here. The reason why the input tiles may have not been completely consumed depends on the values of the lists, right? That of the elements, the values of the elements from lists A and B that are in shared memory. Imagine that all elements of this tile are smaller, are lower, or equal to all elements of this other tile. What that means is that we are going to copy all these elements to the output, but we don't even touch the elements of the other tile. So in the end, in the worst case, we are only copying half of the values to the output, half of the values that we loaded into the shared memory to the corresponding locations in the output. So that's why we have to keep track of how much of the tiles we have really consumed, and then start loading from there. So in this case, we are going to load again one whole tile from A, one whole tile from B. This is from block 0, this is for block 1, and so on and so forth. The problem here, as you can observe, is that we are reloading, we are accessing again elements that we read once, place them into the shared memory. Now we forget about them and read them again from global memory and place them again to the shared memory. So in the end, there are some elements that we are accessing twice, and unfortunately wasting the memory bandwidth. So this tile merge kernel has pros and cons. Among the pros, that we have coalesced loads for the input elements. This way we have reduced global memory traffic for the current functions. We have thread level current functions that are done in shared memory, and we can also have coalesced stores if the output tiles are generated in shared memory, as we briefly explained as a potential optimization. However, the main con or drawback of this tile merge kernel is that not all the elements of the input tiles that we load into shared memory are used. So in the worst case, only half of them are used, and we will need to go to the global memory again to read the same elements that were read before. So that's why we want to propose a more let's say, sophisticated mechanism to keep the tiles into the shared memory that is based on circular buffering. It's a more complicated, more sophisticated data structure, but as you can see, it's going to give us further efficiency in the memory accesses, because it avoids that we have to reload elements that were previously loaded into the shared memory. So let's start from arrays, lists A and B in global memory. We also have allocated the space in the shared memory, this AS and BS. So we start loading one tile from A, one tile from B into the shared memory, and we define what's the point where the buffer starts. In this case, we have these variables AS start and BS start that are equal to 0 in the very beginning, in this very initial step of the operation. So after consuming some of the elements from AS and BS, we update AS start and BS start. And now we know that because all these elements here and all these elements here have been consumed, we can reuse these shared memory locations to keep loading values from A and B. However, we are going to maintain in the shared memory these values here and these values here that have not been consumed. So what we do is go into the global memory, reading from the global memory a piece of A and a piece of B that are of the size, the tile size available in the shared memory. So we read them and place them in the corresponding shared memory locations. So this is where we start with the next iteration. Observe that now threads will have to start searching for values in these tiles where the corresponding pointer AS start or BS start indicate. So in the next iteration, probably the threads consume this part here for array AS, and for BS, this part here, and we update the AS start and BS start correspondingly. This is the code for the for loading the circular buffering tiles. In the beginning, the AS start and BS start is equal 0, and in the beginning, the whole tile size that we can load from global memory into the shared memory. We are going to perform, as you know, from before, from the previous tile merge kernel, number of iterations that is controlled by this counter here. First of all, we load or refill AES consumed elements into AES, depending on what's the value of AES consumed and BS consumed. We are going to load more or less elements into the specific area of the shared memory, AES or BS. This is for AES. This is for BS. Observe that in both cases, we are loading as many elements as free positions we have in AES and BS. Now there is one challenge here when handling this complicated data structure is the fact that in the circular buffer, the tiles wrap around. And what that means is that we may need to compare to a higher ranked element, higher ranked value of A and D or B that may reside in a lower address memory location in shared memory. So in the end, this makes the handling of the current values more complex. In reality, as I said, we may have initial values of AES start and BS start that are here, and for one particular thread in the thread block that is using these two tiles, the A current and A next indices might point here, in this case, in the case of AS. However, in the case of BS, because the tiles wrap around, you see that B current is actually a higher index than B next. This entails a challenge because, for example, if we want to calculate what's the size of the section or the subsection that one particular thread is going to work on, in the case of, in this particular example for AES, we can simply calculate this size as A next minus A current. However, in the case of BS, we have to take into account the fact that B next is a lower index than B current. So in that case, we would need to calculate this size from here to here by using this expression, B next minus B current plus the tile size. In order to operate, to handle the data structure, the circular buffer in a simpler way, what we propose is, what the particular implementation that we are discussing here proposes is a simplified model for the current values that assumes that the indices don't need to wrap around. They simply continue increasing, and even though the size of the tile is certainly limited, what we do is like obtaining kind of virtual current values such that B next or A next is always greater than or greater or equal than B current or A current. And this way, we can always calculate in this example the distance between both indices using the same expression, B next minus B current. And this is how the code looks like. Remember, this is actually the actual code where we divide the output tile among the available threads in the thread block, and then each individual thread block calculates or obtains A current, B current, A next, and B next. To do so, we just need to change the way that we call this core rank function. In reality, there is not much difference if you compare this code of the circular buffer merge kernel with the original tile merge kernel. It's essentially the same code. Mainly the calls to the core rank and merge sequential functions change, but not more than that. And more or less it's the same for the final part of the while loop, where we update the consumed and completed variables that keep track of the part of the input arrays that have been consumed and the parts of the output array that have already been written. So interesting observation here is that, as I said before, only the sequential merge and core rank functions change, essentially this implies that a well-designed library interface, such as the one in this particular example, limits the impact on the user code. The thing that we really have to change internally is the core rank function, in this case, the core rank circular function, where, as you see, we are using this I circular, this IM1 circular, J circular, and JM1 circular that wrap around based on the what's the tile size. And we need them, we need the exact values of them in order to access the correct values from the input sections of A and B. But in the end, the binary search here is exactly the same, obtaining delta value and then updating the corresponding variables I and J, depending on what's the condition that is fulfilled here. And this is the sequential merge for with circular buffers. Again, you can observe that the code itself of the algorithm doesn't change. It's only that we have to use this I circular and this J circular in order to access the right elements from the tiles in A and B, taking into account that the indices in reality wrap around because the limited tile size. So that's essentially it. As a summary, merge sort is a really important primitives in some algorithms, like sorting algorithms, for example, also very important for map-reduce frameworks. The parallelization of merge sort requires each thread to dynamically identify its input ranges. That's what makes this implementation challenging, but also extremely interesting. The input ranges are data dependent, as we have seen, and there are also challenges when using tiling, because of the fact that we may need to reload elements that were previously loaded but not consumed. That's why we propose the use of circular buffers, even though it's a more complicated data structure, more sophisticated data structure, and as you have seen, it implies more complex calculation of the indices to access data from the shared memory. However, we can use a simplified buffer access model to not increase the code complexity that much. This is all for today. If you want to read more about this merge sort parallel pattern, I recommend you chapter 11 in the book Programming Massively Parallel Processors. And yeah, thank you very much for your attention, and I hope to see you in the next lecture of our course on heterogeneous systems.